Have you ever just stopped to wonder why the physical world around us actually holds together at all? Welcome to this explainer. Today, we're going on a really fascinating journey to uncover the hidden lives of everyday materials. We're talking about the secret, invisible battles happening inside the metals, plastics, and structures that we rely on every single day. And don't worry, we're going to totally bypass the heavy math and dive straight into the core concepts to find out exactly how and why things break. Let's start with something you've probably done, 100 times. Think about a standard metal paper clip. If you take that tiny piece of wire and just bend it back and forth, eventually, snap, right? But why? You aren't really strong enough to just pull solid metal apart with your bare hands. So what is actually happening at the microscopic level that causes it to just give up and break? To understand that, we need to look a little beneath the surface. Section 1. The invisible internal battle. Okay, let's dive right into this. Before a material actually breaks, there's this massive, unseen conflict happening right inside of it. The materials all around you aren't just sitting there. They're actively responding to the world. Engineers measure this battle using two absolutely crucial concepts: stress and strain. Imagine stress as the invisible internal pushback. It's the material's way of digging its atomic heels in and resisting whatever outside force is messing with it. Strain, on the other hand, is the visible physical stretching or squishing. It's the actual shape change that happens because of that force. So stress is the internal fight, and strain is the physical result. Makes sense, right? Section 2. Bouncing back versus permanent change. So what's actually happening to the atomic structure when we start pulling on these materials and causing that strain? Well, materials basically have two very different ways of reacting. First up, we have elastic deformation. Just think of a rubber band. When you stretch it a little bit, the atomic bonds inside the material are just stretching out. They're acting like billions of tiny little springs. The absolutely key thing here is that there's no permanent rearrangement of the atoms. As soon as you let go, boom, it bounces right back to its original shape. No harm done. And this brilliantly illustrates exactly what we call Hooke's law. It's basically the perfect bounce back zone. Notice how, in this elastic phase, stress, our internal pushback, and strain, the physical stretch, grow together in perfect harmony. It's literally a direct relationship. If you pull twice as hard, it stretches twice as much. Let go, and the material slides perfectly back down to zero. But what if we pull a little too hard? Well, that's when we hit plastic deformation. This is a point of no return. The invisible atomic bonds don't just stretch anymore. They actually break and slip past each other. The entire crystal lattice inside the material permanently rearranges itself. Think of a car's crumple zone in a crash. Once it crushes, it's forever changed, right? It's never going to independently bounce back to its original shape. Section 3. The journey to fracture. So what does this actually look like when we take it to the absolute extreme? We're going to trace the dramatic, high-stakes narrative of a material pushed past all its limits, right up until the bitter end. Think of this as a roadmap showing exactly how a ductile material like steel or copper fights back before ultimately failing. We start out safe in our steep, elastic bounce-back zone, but as we push harder and harder, the material goes through some major structural crises. The very first major crisis is the yield point. This is literally the exact moment a material stops bouncing back. It crosses that invisible threshold from elastic to plastic. From this exact spot onward, any damage done is permanent. The material's internal architecture is now forever altered. So, the crucial point is right at the peak, the ultimate tensile strength, or UTS. This is the absolute maximum pushback the material can possibly muster. It is giving everything it has to hold together. But once it passes this peak, the material starts something called necking. It physically thins out in the middle, almost like pulling a piece of taffy apart. And at that point, total failure becomes inevitable. Which brings us to the tragic conclusion: fracture, the literal breaking point. This is the exact moment those atomic bonds completely sever and our material physically snaps in two. The internal fight is officially over. Section 4. Fatigue, the silent killer. Now you might be wondering, everything we just looked at assumes we're pulling a material harder and harder until it pops. But what if I told you a material could fail way below its ultimate strength? Like, can materials get tired just like we do? If you aren't applying a massive crushing force, are solid objects perfectly safe forever? Well, the surprising truth is, no, they aren't perfectly safe. We call this fatigue. It's the progressive failure from repeated, everyday cyclic loading. This means forces well below the maximum strength can still destroy a part if they just happen over and over again. And hey, that solves our paperclip mystery from the very beginning. The paperclip breaks not because you're super strong, but because the repetitive back and forth bending causes fatigue. You're slowly creating tiny microscopic cracks, destroying its internal structure with every single wiggle until it finally snaps. Now, what's really interesting here is the terrifying difference between two everyday metals, steel and aluminum. Notice how with steel, the data actually flattens out. That means if you keep the stress below a certain point, which engineers call the endurance limit, the steel will basically last forever. But with aluminum, it never flattens out. The trend just keeps dropping. That means aluminum has no true endurance limit. If you bend it enough times, even slightly, it will eventually fail. Engineers have to plan for this constantly when designing the aluminum bodies of airplanes. Crazy, right? Section 5, Pushing Materials to the Limit. So, how do we actually know all this? We don't just guess. Engineers have extremely clever and, honestly, pretty destructive ways to force materials to reveal these hidden secrets in a lab. Meet the ultimate truth teller, the Universal Testing Machine, or UTM. This towering piece of equipment is designed specifically to pull things apart, crush them, or bend them, all while precisely measuring that invisible battle of stress and strain we've been tracking. Let's see how this builds in an actual test. It's surprisingly brutal, but beautifully simple. First, they grip a piece of the material, often shaped kind of like a dog bone. Second, the machine slowly pulls it at a constant, steady speed. Third, the computer continuously records the exact force being applied against how much the material stretches. And finally, the machine just keeps pulling without mercy until the specimen fractures completely. By running tests like this, engineers aren't just looking for raw strength. They're looking for toughness, which is the total amount of energy a material can absorb before it breaks, kind of like a boxer taking a punch. And they also look for ductility, which is a material's ability to stretch and deform before it snaps. This is so vital. A highly ductile steel bridge will sag drastically before it collapses, giving people a visual warning and time to escape. A non-ductile material, it would just shatter without any warning at all. So the next time you're out in the world, just look around. What invisible battles are happening inside the steel bridges you cross, the concrete buildings you work in, or the aluminum planes you fly in every single day? The physical world isn't just sitting there passively, it is constantly fighting to hold itself together.